All right, hi everyone. Here is a video to help with the last question on your homework with the tennis ball falling and you're trying to plot terminal velocity. Okay, so here is in the black equation, that is, we have weight, we have drag, and we have inertia. Okay, so sum of the forces equals ma. I wrote it into what they call a differential form. Okay, so this solution, okay, we can actually find a solution numerically. Okay, so what I want you to do is look up online or look up somewhere the mass of a tennis ball, the coefficient of drag, and the area. Okay, so what you need to do is, oops, come on, why? There we go. Sorry, is just rearrange that equation. So you have dv dt equals g minus 1/2 rho v squared cd a over m. Okay, and this is first order. Okay, in order to solve this, okay, you actually need another equation, which is dx dt, which is equal to v. Okay, because I want to solve for the position too, not just velocity. I mean, you could just use this one, but I want you to also solve for the position of the ball, right? Because in a differential equation, okay, whatever's to the right of the derivative, so I circled the v, is what you're looking for. You're looking for velocity. Okay, down here, you are looking for x, or position. Okay, so we're going to assume this ball falls straight down. All right. So in week 9, I go through this. Week 10 is a great video you should watch about numerical methods and how you can solve this. Okay. All right. So really pay attention when I start at 1640, because that's how I want you to model the code. Okay. So what you need to do is, here's kind of an example code that you can kind of follow. So you're going to write your givens. So the density, the mass, the area, the coefficient of drag, gravity, your time step, your total time, and this is a matrix. Okay, and this is very similar to in the video that I made. Okay, now I'm setting the initial velocity of the ball to be 0 and the initial position to be 0. This line right here is just putting both initial conditions together. Okay. The for loop that's in the video is exactly the same. Okay. All right. So you can just write that down. Okay. And then after this for loop, I start plotting. All you have to do is, after this change, just change theta to v and omega, or w, to x. Okay. Then you can go into your function code and make the function code. Okay. It's really the first line in the function code that you'll see. It's around 22 to 23 minutes, okay, in the code, in the video. It's the same, okay, but then you can put the mass, the area, the drag, gravity, and the density. You can put them all right here, okay? When you make a function file, you have to make sure that this file is named whatever this is, and it's saved in the same location that your main code is in, okay? Otherwise, it will not work. Okay, so you'll see that I changed like omega and theta to v and x. Okay, then you're going to put your equations. So dv dt is the equation above, okay, which is this one. That's what you put in there. Okay, and then the next equation you'll see is dx dt equals v, and that's what you put. Okay. So dx dt equals v. And then you'll see that I have the solution underscore dt is dv dt dx dt. So basically what's happening is I'm solving both of these equations, these differential equations, simultaneously at the same time. Okay. So then you save this. You can go back to your main code and run it, and it should give you a graph, okay, where the velocity increases and then levels out. Okay, that's your terminal velocity. So when the drag equals the weight, because you're no longer accelerating anymore.